Hello, thanks everyone for attending my talk. I'm Nicholas Brunhart-Lupo. As I mentioned, I'm a scientist at the National Renewable Energy Laboratory, and I am here to talk to you folks about our work that we've been doing in collaborative exploration of scientific data sets using immersive and statistical visualization. This is a talk from a paper that we did that we submitted to SEA ISS last year. We're just getting around to the talk now, thanks to COVID. So let me get started. All right. So in this talk, I'm going to go over first a little bit of background by what I mean by immersive and collaborative visualization. I'm going to do a little bit about our first contribution, which is a little taxonomy that we've created to help contextualize these kinds of systems. And then I'll move into our second contribution, Plotty VR, which is our answer to collaborative visualization. And then I will go over a few use cases that we've encountered throughout this project. And then I'll talk about some of the future work and future directions that we've got in this space, along with some Q&A. So let's start with a little bit of background. What do I mean by immersive visualization? So immersive visualization is the practice of using things like VR headsets. So we have like models right here. She's wearing an HTC Vive. It's a practice of using these sorts of systems to bring representations of a researcher's data to life and immerse them inside of it. This may also be a system like what you see here. This is a cave-like environment that we have at NREL. You can see a person here wearing some tracked glasses there, and he's looking at this large projected surface. And we use things like stereo systems and these immersive displays to try to give the researcher a psychophysical sensation of being right inside the data to help them get a unique viewpoint of that data. And we have observed firsthand how these systems can really enhance the standard scientific workflow. Furthermore, these systems are, especially the head-mounted displays like the HTC Vive, they're becoming quite commoditized. They're showing up in droves on our researchers' desks, and they're having kind of a hard time using them. And now all these tools, immersive visualization, can provide, unique qualitative insights. They do present a limited quantitative insight to the data, which is, no surprise there. So what we want to do is we want to gain the best of both worlds. We want to glue the quantitative and the qualitative together. The immersive space and the more concrete statistical world, we want to glue these things together so we can improve the analysis products that we are generating, and that the researcher can get a better confidence of what's going on in their data, get a better understanding of what's going on in their simulation. We want to bring these two things together, and that's what we want to call collaborative visualization here. So what I might mean by that is, so for example, let's say we have a user in an immersive space, kind of looking there on the right side of the screen, working around with their data, maybe finding an interesting cluster inside their data, brushing and selecting that cluster, sending that back to an R or Python script to do some more quantitative analysis, maybe compute some new metrics, maybe tease apart some internal structure there, and then bring that back to the immersive space so they can look at even more types of that kind of data, or do some further analysis of that interesting cluster. How to do this? It is very, very hard. Collaborative visualization has been named as one of those grand challenges for visual analytics. There are massive bandwidth requirements, interaction questions, software implementation questions, questions about what works best, so on and so forth. And because of this, it's very complicated. It's out of reach for a lot of users. Even if you own a VR headset on your desk, you may not know immediately how to use that to get the analysis that you want done. So this is an area of intense research. There is a strong focus on shared visual imagery. Now, what do I mean by shared imagery? In this context, where we're talking about all the users of a collaborative system are seeing the same visual representation of the data. So that's what we're kind of seeing here on the left side of the figure. That indeed has value, no question about that. But we also want to enable researchers to see the data in a more heterogeneous way. So we want to have maybe one user, as you can see on the right side of this figure, we can see some folks looking at a geospatial display. Maybe we want to have another user looking at an R display, and then maybe another user looking at it inside an immersive display. and collaborating together to analyze that data. This makes it much, much harder. That's kind of a demonstration, though, of the different dimensions of what collaborative visualization can mean. And so when we started this work, we wanted to do a little survey of the systems out there and the work that's out there to build a sort of initial taxonomy of these kinds of systems. This kind of helps contextualize our work in the larger world, and I think also helps guide forthcoming contributions, and also kind of helps get a good idea of where the industry and the whole idea of collaborative visualization, where that's actually moving as we go forward in time. So let's dig in there. We've identified in this initial effort 8 different categories. Let's start with the first one. Location. This is actually kind of simple. It spans the spectra from co-located, where everyone is standing in maybe the same room, to remote, where everyone is dialing in. Remote has issues with things like needing lots of bandwidth, very fat internet pipes if you're going to be bringing everyone together, low latency networking. Questions about do you need a strong server if your processing is centralized, or do you need strong remote machines if you're going to be doing distributed processing and things like that. For folks in the same room, you have questions like how to facilitate user inputs and interactions, how to target imagery to specific users and things like that when they're all moving around in the same room. Next up is imagery. We split that into constant and targeted. In constant, all users see the same representation of the data. In targeted, representation is designed for specific users or tasks. This has a bit of nuance, as there are some systems like Sage and Sage 2 that allows users to share a single desktop on a big power wall somewhere. We would consider that to be constant imagery. Next up is Viewpoint. That's where in the scene the user is looking. We have 2 classes here. We have independent viewpoints, allow the users to individually explore the data and oftentimes share their viewpoint with collaborators. We have privileged viewpoints that constrains users to see what the privileged user sees. What I see is what you see, with no support for multiple viewpoints. This would be something like a tour, right? So you have a volume rendering on your screen, and maybe you have your other users kind of following you around as you point out the important things. That has its uses. And now we have interaction. Consider a situation where everyone is trying to do filtering at once with maybe an internal queue or something to try to manage that. That would be asynchronous versus a single pass the baton token ring network kind of situation where only a single user can interact at a time. Interaction is related to viewpoint in that the support for independent viewpoints often provides support for asynchronous interactions. Data sources. This category is about whether the environment supports looking at multiple data sources simultaneously. So this could be someone looking at a volume rendering of a material when others are looking at that material spreadsheet. Relating to imagery, multiple dataset support may use constant imagery across all users, maybe target visuals for a single user, things like that. Problems in this category are things like, how do we visually connect data sets if you're using, heterogeneous disparate data sets and manage that at scale? Number of displays, this is pretty easy, single or multiple, but it is important to note that multiple displays may be used in both remote and in-person collaborations. Type of devices. This is separated into its own category to kind of capture the homogeneous or heterogeneous display types. So for example, connecting 2 immersive cave systems, that's homogeneous, whereas connecting HMDs and laptops is a heterogeneous environment. And that kind of situation has become much more prevalent as we're getting these HMDs on desks, tabletop displays, other state-of-the-art displays are becoming a lot more mainstream and a lot more easily accessible to our researchers. Epic. This relates to when the user is collaborating with the system. So most often we're talking about this in terms of real time, where people gather at the same time, they have those personal interactions, but there is a group of work that looks at things like playback of collaborations. That would be useful for things like sharing your interactions with another, or maybe having multiple people doing independent studies that you then later merge into a single cohesive bit of research. So there we go. That's our cute little nice taxonomy. A much more in-depth taxonomy is forthcoming, but this was our first initial crack at it. And here's a list of some of the publications that went into this taxonomy. And we sort of reorganized these so you can see how these works kind of flow into these different things. It's kind of hard to see. Let's turn your head a little bit into these different categories. A lot of the older publications show things like remote locations, constant imagery, privileged viewpoints, simplicity. That was kind of the state of the art in the 90s and early 2000s. But as you go forward in time, you start seeing this shift towards more difficult things where you have mixed presence, you have independent viewpoints and asynchronous interaction. So it's a very interesting thing that we're seeing going on here in the community. So with that contribution, let's get to our other contribution, which is Plotty VR. That's our answer to collaborative visualization that we have at NREL. Plotty VR is a collection of tools that we've been working on to collaborate, to facilitate this sort of collaborative visualization stuff. It's written in C++, R, Python, and Julia. It's a whole set of tools. It's not just a single thing. In terms of our taxonomy, we are co-located, some remote. We are targeted in imagery. We are independent in viewpoint, synchronous, homogeneous in data, multiple in displays, heterogeneous in displays, and real time. Now, what this tool set does is provide a bidirectional link between a Python or R programming language environment and an immersive 3D visualization. So using this software package, an analyst at a laptop can push data into an immersive visualization. And the representation of that data can take the form of simple primitives like points, line segments, which you can sort of see right here on the right side of the figure, or of just images and text. Developing these sorts of visualizations mirrors traditional plot development with just a simple third dimension. So, for example, our users, you can instantiate a 3D scatter plot and an immersive display by just issuing a plot command with 3 arrays, X, Y, Z, and optionally providing point colors and scaling. Furthermore, these plots allow users in the immersive space to probe the space for data values and get annotations out of it. So selection is bidirectional too here. So if you select something in the cave, say that we found a cluster of interest, you can that region is automatically pushed back into the R Python client for them to work with. So it's kind of like what we wanted to get to at the start of this talk. While we were making Plotty VR, we had a few guiding principles that directed the design of the tools, and this we found to be very, very important. Critically, we cannot in any way, shape, or form demand that analysts discard their workflows. Researchers do not like major changes. Even if there's great apparent value to whatever tool you're offering them, if it requires major changes to their workflow, they will not change. So you get common complaints or things like, when you're using peer review or something, how do I get my data and decision flow into this new framework? There may be reasons that they're using their older system, right? Or their other system, doesn't need to be old. They don't want to re-engineer their entire pipeline. So, they have to figure out acceptable formats, right? Scripts to translate data, get your data set out, get your features out, get your decisions out. It's just terrible. So this, I should mention, is also in addition to the challenges of trying to learn how to use an immersive space. So this prospect can be quite daunting. So we want to minimize changes to existing workflows. We also want to reduce friction. All the augmentation that we're doing has to be as friction-free as possible. Even if the package does not require replacing a researcher's workflow, you can really make it intrusive in other ways. So, you don't want your researcher to have to sit down and spend tens of minutes setting up a server, copying data, running scripts, verifying connections, and all that stuff for just a few minutes of exploration. You want this to be as easy as possible for them to just get in and get out. It's got to be as easy as 2D plotting. So to fulfill these principles, we provide our tools as libraries for R, Python, and Julia. You can easily install them through each language's package manager. They're right there. We designed each library to mimic the API of common plotting 2D packages that are within those libraries. If you're already using those APIs, which people typically are, then your data is all ready to go for our immersive plotting system. You can just simply walk into an immersive space and plot. If you're going to use your own VR headset, then all you have is this slight additional step of just starting up a quick server to get a Unity-based server so that you can get your headset working correctly. On a more technical note, we have a standard client-server architecture. We have a client library that speaks some binary packets over WebSocket to the Plotty VR server. And that server uses either Unity or our custom immersive rendering engine that we have at NRL. It's called ISOPAC, and that realizes those plots. One point here, you have to be a little bit careful here when you're using WebSockets or any other socket system. You have to be very careful that you don't take over the user's interactive REPL, their command line as they're using Python, R, or Julia. You want to make sure they still have that interactivity so they can still do things while the plot is going on. It takes a little bit of finesse. So with Plotty VR, we have supporting as first class the common plot types. We've got scatter with certain glyphs, line plots, images, and text, which sounds remarkably simple. You think, ooh, immersive, there should be something really flashy and fancy, but people don't want that. They want the simple things that they know, that they can easily use. And when you take these simple components, our users have actually turned these things into even more complex things. Things like 3D parallel coordinates can be made with these sorts of plots. You can make, in this example right here, in the left side or right side of this figure, you can see a user has made a ladder plot. So they're looking at the deltas between ensemble simulations, and you can create these very complex things with just these simple primitives. Further, since this augments a workflow, it allows for some very interesting compositions to be made. So for example, some users have made web pages in Shiny R, adding custom 2D plots that get loaded into the immersive display on demand. We've had some users who have turned this into much more of an operational sort of thing where they're handling streaming data and plotting that streaming data as it comes in so they can monitor a system. So let's take a look at a few examples of this tool in action. First up is a project called Cities Leap. This is a project we did at NREL that developed city profiles for about 24,000 US cities. This is some of the energy profiles for those cities. And here you can see in this image, we've got an R-based Shiny dashboard that allowed cities to be compared on a range of metrics with the immersive 3D display. In the image, you can see the little Shiny plot there on the user's laptop. You can sort of see they have their own little plots going on there. And the person in the immersive display is looking at cities plotted by different emissions types. And the user is currently probing a value with that little controller there. He's looking at Los Angeles there. He's pulling out a city to find out a little bit more information about that as compared to how much emissions they're generating. And that selection he's making right there, it's really hard to see in this picture, but that's being pushed back into the Shiny R interface so that they could see what's going on in their other 2D plots. And he and his team, they would iterate on this, hypothesizing on relationships and generating new metrics as they look through different data sets and different portions of the data sets. And then they can ship these metrics to the plot to test those hypotheses. You can also see in the immersive display in the top right corner there above Los Angeles, a copy of some of those plots in the Shiny interface. You can move those images up there because we can plot images. And if you generate an image, we can put it in there. Another one is with self-organized maps. So this is a user that did some similar work with Shiny to create a Shiny web application to explore some self-organized maps of ensembles of high-dimensional simulation output. So the web interface here that allows analysts to manipulate the parameters of the dimension direction algorithm and to view 2D projections of the maps on their laptops. So that's kind of what you would see in the Shiny interface, but they'd also want to be able to push these maps into the immersive space. That's what you're seeing there on the right is the immersive representation of these organized maps. And this was really, really neat because we were able to have some users with the Shiny web interface. They were in a different city than the immersive display. So we had users using their two different interfaces separated by thousands of miles collaborating on the same data set. That was really neat to see. This application also had a parallel coordinate system developed in a web VR client. So they were able to tie together a user's laptop, the immersive space, and this other VR experience all together in one single, analysis system that they brought together, and these systems were all reacting to each other. So it's really neat to see that and have that collaboration happen with composition, because that's what we want to do. We want to augment, not replace. We want people to be able to glue what they need together and create the experiences that they want. In some other cases, we've had people who have taken 2D wall projectors next to the immersive space to even further improve decision making and improve the environment the way they want. So what's next? For Plotty VR, we'd like to release the server for more graphics platforms. Like I said, it supports 2 at the moment, but there's no technical reason why we can't do more. And we like to release the libraries for the languages. We have packages already for Python, R, and Julia. We'd like to release those to the official package managers. Right now, they're internal, so that everyone can use these wonderful tools. Inside Plotty VR, technically, we have discovered a few limitations that have made themselves known. First, it was designed for a single client, single server. That has not stopped users from patching in other sort of clients. Like I said, for the self-organizing map example, they were able to bring that in, but they had to do all that work by hand. It was very manual. There's a lot of legwork. A lot of users are not going to do that. That was an exceptional user. And as implemented, the server has to be graphical. The client has to be a REPL kind of a thing, and that has some limits. So in response, like I said, this talk, the paper we wrote was a year ago, and we've been working on this. It's a revision to Plotty VR called Noodles, the NREL object-oriented data layout and exploration system. We like our acronyms. At the core, this is a protocol specification. So that's all we're really trying to specify here is a protocol for tools to synchronize visualizations with a few reference libraries and server libraries. We think this will enable folks to write their own visualizations or have our team write some for them. And any tool that can talk this protocol can join in. That means we can have Python clients, Unity clients, immersive graphics engines, scripts, web clients, whatever. If you talk this protocol, you can join in the collaboration. And we're targeting that Noodles will cover a bit more base cases, providing asynchronous interaction, and it should also permit playback so that people can record and share its sessions. And with that, I'd like to thank folks for listening, and I'd like to move to questions and answers.